Back in the 90s, before the internet was really a thing, my father bought this book on computer-generated fractals with a disc in the back, which we used to make colourful images. Of course, the first one we always did was the traditional Mandelbrot. What amazed me was the complexity and chaotic nature of the edge for such a simple formula. At the time, the book gave some quotes for calculating the picture, and these were on the smaller screens, but 40 minutes to an hour for 386 computers to see our output wasn't uncommon. With our more powerful 486, we could see the output in just 5 or 6 minutes. Nowadays, this image could be made between frames. Computers can easily do the calculations required in the blink of an eye and at much higher resolution. But limited by the technology, there was a lot of effort into learning how to optimize the calculations, how to get the image done by doing less work. These techniques have applications even today. Because processing power is still finite, but data sets are getting bigger, and the cost of processing is not just measured in time, but in power, energy, and the heat output of the work. For all these renders, the system has been purposely slowed down to show the rendering process. When rendering for a screen, we have an obvious quantization of the data. Each pixel's location is resolved to a coordinate in the complex space, and that is used as the starting element for the Mandelbrot formula. We put the values in and get an output, a second coordinate in the complex space. The question for Mandelbrot is, if we keep putting results in, does the path eventually leave a circle of radius 2, or does it stay inside? And if we're colouring, we assign a colour depending on which step it leaves the circle. For these pixels, I'm just colouring red if it has left and white if it's still inside after 25 iterations. But it means for each pixel there is potentially 25 calculations, and with 19,020 by 1080 resolution, that means there's just over 2 million pixels, or a possible 50 million calculations. The first optimization is to stop it when it reaches the radius of 2, and once it's left it will continue to spiral outwards. The next technique that I love to use is boxes. We draw all the pixels on the outside of the box, and if they're all the same value, we assume everything inside the boxes as well. If not, we divide the box in half and repeat. By keeping track of which boxes we have and haven't done, and by rendering the edges of the boxes in a different colour, we actually get a different picture, and already the chaotic nature begins to show. This actually can be done in two different styles: big boxes first or smallest box first, top down or bottom up. Both result in the same picture at the end, but have different aspects when we reach the render. And what if we didn't actually have a digital screen? What if we wanted to physically draw the fractal and weren't limited to quantizing the pixels? Well, this next method works well for fractals to have a continual edge. Firstly, you move out from the central point to find the edge, taking each step until the edge is found. At this point, you mark that point, then pick points on a radius from there, finding the next edge point and path. The accuracy of this method does depend on the size of the radius of these circles and the angle between points. But if physically drawing, as long as that radius and angles is similar to the size of your pen or brush, then the error will be unnoticeable. By carrying this out with some other optimizations, it's possible to generate a whole new look of the fractal generation. And with randomizing the sizes to get around certain calculation issues, we're able to work out the edge of the fractal with a fraction of the total calculations. Comparing these methods synchronized in the calculation clock, you can see the edge detection method is superior to the other two, but the actual performance does vary on its starting conditions. All three methods here and others have benefits for performance, and there are issues of artifacts or missing elements, but the end result is a blend of art and science. The Mandelbrot set as a fractal image is famous and very distinctive. You'll probably begin noticing it on film and TVs when they want to suggest something is complex or chaotic. For me, it's always been a reminder of looking at these things with my dad and how complex and things in the universe can come from simple things.